Good morning, everyone. I am very happy to be here. I arrived with 10 minutes to spare. There was a little bit of chaos at Schiphol Airport. It's good to be in Manchester. I actually grew up 35 miles from here in a small village, Skelmersdale. There is no LINX pub there yet, but who knows? Today I want to update you on a project I've been collaborating on with LINX and various other large internet exchanges to develop the next generation of route servers for route serving. In this talk I'll cover briefly what the purpose of route servers is, why they are important, what challenges currently exist in the global internet exchange ecosystem, the structure of a foundation in which we attempt to overcome this challenge, what we've accomplished so far, and what we are about to engage on. So, what are these route servers? Route servers are like walking into a pub and the hostess tells you, this is your new group of friends, just sit at their table. And immediately, just like that, you get to exchange and communicate with a bunch of fellow-minded people. Route servers are a rendezvous point of sorts. You send BGP route messages towards the route server, and in turn, the route server will redistribute all these BGP updates towards other participants of the same route server. And in doing so, you can achieve a few advantages. Route servers lower the barrier to entry for an internet exchange point, because from the get-go, you can exchange routes with a significant number of participants of that internet exchange fabric, and in doing so, make your interconnection more valuable from day one. Another advantage is that it can reduce operational cost for organizations, in that you don't need to busy yourself with provisioning or decommissioning of new BGP sessions as people enter or join or leave the internet exchange. And finally, you benefit from centralized expertise. Route servers nowadays are well-managed services with stringent filtering, and the LINX staff or the internet exchange operator can help in troubleshooting why sessions are not working as they should, or why routes are not propagating as they should. And in doing so, they reduce the burden on the internet exchange participants. So in short, route servers are a mission-critical service for modern internet exchanges. And with that in mind, let's dive into a challenge that exists. As it stands, there is only one popular BGP implementation that is capable of meeting the highest requirements of large internet exchanges. That is the excellent BIRD project. However, this puts us as an industry in a similar situation to what we had more than 1.5, 2 decades ago, where all DNS name servers were running bind. And if there ever was a security issue with bind, well, shared misery is double misery, but it affected everybody. And having a monoculture around one specific software implementation has tangible downsides, specifically in the realm of security issues, but it also can lead to situations in which innovation is somewhat stifled because a lack of competition is not always the most inspirational standpoint. So, and then finally, relying on a single implementation puts an incredible pressure on the teams that have to operate that implementation, because it requires flawless operation 24/7 with 100% uptime, and this is quite hard to achieve in software engineering projects. Whereas if you approach it from a more diverse perspective and have 2 independently developed implementations, it somewhat mitigates the requirement for either one of those implementations to be absolutely flawless, because the chances of 2 implementations suffering the same bug at the same time is very, 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 very small. So this, the project I'm talking about set out to make life easier for the operators of internet exchanges, and in doing so, improve the robustness and resiliency of the internet exchange platform for all of us participants. So the recommended model that we're heading towards is that per peering LAN, you end up with 2 route servers that operate entirely independent from each other in an active-active configuration where one is BERT and the other is OpenBHPD. So what's behind the effort to make OpenBHPD suitable for carrier-grade operations? In 2020, we started a unique collaboration amongst the world's largest internet exchanges. I don't think there are many projects of this scale in terms of engineering effort and goodwill that the founding sponsors, LINX, DKIX, M6, and NetNode put into this. Rssf, the Route Server Support Foundation, is a non-profit foundation registered in the Netherlands. And this is the legal vehicle through which we hire talented developers and collect feedback and provide support to internet exchanges. The structure of Rssf is as following. We have a board of directors. I am one of the directors. The board of directors has fiduciary responsibility and is in charge of hiring staff to do the actual work. And then we have 2 interesting aspects to this institution to facilitate proper governance of the nonprofit foundation. We have the TAB, the Technical Advisory Board, and Tim and Mo are part of that. And each internet exchange sends a technical representative to who participate in monthly calls and from whom we collect feedback or provide support to how to use OpenBHPD. And then separately, at more of a C level, there's the supervisory board. Richard Petrie is the representative from LINX, and the supervisory board provides oversight to the board of directors in terms of whether the institution is financially healthy and whether we are on track with our long-term strategy. Now, how do you ensure success in a project like this? Because building a route server is no simple feat, and having a project maintain high quality over time requires a few checks to be built into the development process. So first of all, our developers are equipped with advanced machinery on which they can run so-called synthetic workloads. This is mostly composed of virtual machines that are fed MRT dumps to emulate the internet exchange environment and see how the software exactly is performing under duress and building, for instance, flame graphs to understand what exactly are performance bottlenecks or where certain software is performing well. OpenBHPD is part of the OpenBSD project. You may know this project for tooling such as OpenSSH, which I bet many of you use on a day-to-day basis. And the OpenBSD project imposes stringent requirements on any contributions in code. For example, it has to adhere to certain development styles. We adhere to concepts like privilege separation to reduce the blast radius of potential security problems. And last but not least, we adhere to at least 4 eyes principle. So every contribution to OpenBHPD or the OpenBSD project is peer-reviewed by people knowledgeable in that particular field, and without sign-off of developers that are your equal or better, code cannot make it into this code base. Then the OpenBSD project also has a regression framework as part of its source code tree to prevent reintroducing bugs once they are discovered and to ensure the correctness of the software. And then finally, there's a third party that also helps us with quality assurance. in the form of the Routeserver project. Routeserver is a Python-based configuration generation tool, and it supports generating configurations for route servers at internet exchanges with a myriad of features. So on the one hand, it generates configs, which is very, very useful because writing those configs by hand is terrible, tedious work. But a route server also has extensive routing policy regression pipelines. This means that every time there is a new release of the software, it is pulled through a quite extensive pipeline in which we confirm that all the features that route server participants are using still work as intended. So for instance, a community that triggers a prepend on outbound, or a community that lowers the local preference. What these pipelines do is they spin up BGP instances, inject routes with various specific characteristics, and then sort of catch the boomerang as it comes out of the route server and validate whether the properties of that particular route announcement were modified or not modified according to specifications. And this serves two objectives. One is to confirm that all functionality that route server participants use actually works as intended. And secondly, to establish whether feature parity with BERT also is meeting our expectations. So these four steps, I believe, are very productive in ensuring that OpenBGPD behaves as we want it to behave in internet exchange environments. So we started mid-pandemic. I can assure you that kicking off a project of this size without the ability to meet face-to-face is challenging, but we launched and were able to make great headway in extending OpenBGPD with various cool features. So for instance, a feature was added to mitigate the so-called path hiding issue that can exist at internet exchange route servers. Path hiding is a conceptual issue in such environments because the BGP protocol asks you to only send the best path towards a given eBGP peer. And if there are multiple paths, for instance, there's a network that exists behind two LINX participants, and both LINX participants announce that route to the route server. The route server can only propagate one of the two paths. And if that path, for say policy reasons, is not propagated towards a specific peer, maybe the peer indicated that they don't wish to receive routes from one of the two originators, you risk losing visibility of that destination entirely if the route server does not take additional steps to iterate through all available paths and trying as hard as it can to announce at least one path. So this problem is described in RFC 7947, and OpenBGPD is not susceptible to this issue. I see a small typo. We implemented support for the RPKI to router protocol. This allows you to connect OpenBGPD to RPKI validators such as Fort Routinator or RPKI client, and absorb validated payloads from the global RPKI database, and then use those cryptographic attestations to make routing decisions. Another cool development that we are trying to guide through the IETF working group that governs the BGP protocol is a concept called Sendhold Timer. It is possible between BGP speakers to end up in a situation where you have a lack of progression in processing BGP updates, because a BGP peer could advertise a TCP receive window of size 0 towards its peer, and this would block the other side from sending new BGP information, such as updates, or more importantly, BGP withdrawals. And it's very curious. Most BGP implementations do a sort of deduplication of their outbound queue, and this can result in a scenario where you keep rescheduling to send the keep alive, but the keep alive never makes it across the wire, but the BGP session stays up, which in turn means that you are operating in a still mode that could result in blackholing. And to overcome this challenge, OpenBGPD's developers came up with a novel concept, Sendhold Timer, and this means that the BGP daemon keeps careful track of whether writes to the network actually succeed, and if for the duration of the hold timer this does not succeed, the connection is killed, and this means that the still routing scenario disappears and reconvergence can happen for all participants. So this is an interesting phenomena because the patch is only 20 lines, but it can avoid quite disastrous scenarios. The FRR project copied this idea, and with that we have 2 implementations, which should make our chances of success in the IETF much higher. Other cool extensions that happened is support for enhanced route refresh. In the original route refresh mechanism, there was a tiny oversight. You could request your peer to send you again the table of routes that they had queued for you in the direction towards you. But the original specification failed to put in something into the protocol to mark that you received all routes. There was no end of RIP marker. And this tiny oversight was addressed through enhanced route refresh, which is now supported by more and more BGP implementations, including OpenBGPD. What we also did was we added JSON outputs to all show commands. So this means that you as human operator can inspect the state of the daemon, the state of inbound or outbound tables, not just in human readable format, but also structured in a way that is easily digestible by computers. And this output is non-blocking. This is an important feature because you wouldn't want the existence of a public looking glass to somehow interfere with operations of the route server itself. And this format was then picked up by the Alice Looking Glass project, which we extended to support OpenBGPD next to its current support for BERT. And this looking glass is what is used by LINX and many other internet exchanges. So this means that for internet exchange participants, the same familiar interface can be used to troubleshoot propagation of routes. We also added preliminary support for add path in the receive direction, and add path support in the outbound direction is forthcoming. And then finally, we included a mechanism in the configuration that exists on disk to include the expiration timers that stem from the RPKI database. And this is a very useful feature in context of a route server being offline for a few hours, a few days for maintenance or hardware failure. And the moment it comes back online, it will not make routing decisions based on outdated RPKI information because each RPKI entry is marked with an expiration date. So this is like putting a do not consume date on a carton box of milk to avoid you getting a foul taste in your mouth. There we go. Future outlook. OpenBGPD is a rock-solid foundation to build Internet Exchange route servers on, and it is deployed by various Internet exchanges throughout the world. It has all the features that an Internet Exchange route server needs, and this is confirmed through the A route server project, but it has been somewhat lacking in performance. This is why OpenBGPD like a decade ago was fairly popular at internet exchanges, but as internet exchanges grew in size, the development at that time was not keeping up with the performance requirements of large internet exchanges, and this is the #1 priority for the Rssf project to take this beautiful foundation in the OpenBHP source code and now apply speed enhancements and tune to the maximum to make it suitable for even the largest peering lens, such as LAN1. Other features that are forthcoming are Snmp support, so that OpenBHPD can be integrated in existing network monitoring systems, BMP support, and for example, a very recent RFC, BHP Open Policy, which is a feature that helps participants of route servers understand that the other side of the eBHP connection is in fact a route server, and if both sides are expecting to be client plus server, then the session can establish. But if there is a mismatch, for instance, if one side thinks that the route server is a downstream customer, the session would not establish if this RFC is followed. So this is a safety mechanism that I expect to gain some popularity in the years to come. Now, OpenBHPD at LINX. It is happening. And I think that is not correct English. I think I should have added an apostrophe here. Well, you can see I'm not a native English speaker. The plan is to deploy OpenBHPD first at the smallest internet exchanges, because as counterintuitive as that may seem, those are actually the hardest, because going from 0 to 1 means that your internal monitoring processes, provisioning processes, deployment processes, support all need to accommodate this new software package or new vendor, so to speak, in the network infrastructure. And starting at the smallest exchange will make it easier to guide this project towards a successful deployment in the entire fleet. So end of June, Scotland and Wales are scheduled to go first. And based on those experiences, we'll extend the deployment to other LINX-operated internet exchanges. And now we've arrived at the end of what my monologue is going to be. I am open to questions from the audience or any specific details you are interested in. If you don't have a question right now, you can always reach out to the project through hello@rssf.nl. And on our website, as we consider ourselves to be a transparent nonprofit foundation, you can find annual reports that we'll publish every year that include overviews of our finances and technical accomplishments. So with that, open microphone.
Okay, does anyone have a question? Neil has a question.
Hello, Job. Long time no see. Snmp, really? Can we do something more modern? Do we really need to put all this old code into something like this?
That is a great question, and I've spent many hours contemplating what would be the best mechanism to send telemetry from a daemon like OpenBHPD to network operating systems. I consulted with a number of experts in the field, for instance, Paolo Lucenti, who is on the forefront of what streaming telemetry is and will be. But eventually we concluded that Snmp, backed by Agent X, I don't know if you're familiar with that protocol, but that's a protocol that can be used to not only create Snmp context, but potentially also create other types of telemetry output. But we concluded that in this day and age, 2022, Snmp, for the purposes of monitoring, still is a very viable choice, especially given the existing deployment footprint of Snmp libraries. So I understand it sounds a little bit old-fashioned, and maybe in 5 years' time the playing field will be different. But for now, Snmp seemed the best choice to start somewhere, so to speak.
Okay, any more questions? Okay, well, thank you very much indeed.
Thank you so much, and thank you, LINX, for participating in this project. I am humbled to be able to be given this opportunity to build route servers, and I'm very excited to venture into real-world deployment. Thank you.
Yeah. Thank you, Joop.